In this tutorial, we're going to look at the atmosphere, the first aim being describe the current composition of the atmosphere, that means the balance of gases that make up the atmosphere, then describe how the Earth's atmosphere has changed over time, and then look at the evidence that supports our atmospheric composition. Now, the atmosphere is fairly easy to take for granted, very easy to ignore because it's pretty much invisible. In fact, you can only really appreciate its beauty when you look at it from space, where you can see it as a thin blue pencil line that surrounds our planet. So the atmosphere is just a mixture of gases that swirl around our planet's surface. When you wave your hands through the air, you're cutting through the atmosphere. There's approximately 1.5 million tons of gas that actually makes up our atmosphere. We live in a sort of warm, nice soup of gases called the troposphere, which is about 15 kilometers high. Beyond that's the stratosphere, and that's where your aeroplanes will fly. And then above about 30 kilometers, it pretty much looks like space, but actually the atmosphere keeps on going for quite a distance beyond that. But the atmosphere, like ourselves, has had quite a journey. It didn't start off this way. So let's look at how the atmosphere has changed over time. Well, at present, there are three gases that make up the majority of our atmosphere. The blue part of the pie chart represents the gas nitrogen, so 78% of our atmosphere is accounted for by nitrogen. The pink part of the pie chart represents oxygen. Yet 21% of the atmosphere is represented by the gas we need to survive. And finally, that thin sliver of the pie chart represents the gas argon, of which there are other trace gases. The one you need to know is carbon dioxide. Carbon dioxide takes up about 0.04% of that 1%. You have to memorize these percentages because they can test you on every single one of these, even 0.04. So that is the current composition of the atmosphere. So where did these gases come from? Well, our Earth started off as an incredibly hot ball of molten rock. Any gases or any sort of atmosphere, such as water vapor, would have instantly evaporated and just escaped into space. Before an atmosphere could actually develop and stick to the surface of our planet, the Earth needed to cool down. It is also thought that during this molten semi-solid state, a comet, basically a frozen ball of ice, plunged itself into our planet's surface. Some scientists believe that this comet is the source of the water that currently exists on our planet. So this is the first part of the story of our early atmosphere. Volcanic activity was responsible for basically pumping out carbon dioxide and water vapor into our atmosphere, mainly carbon dioxide, possibly some methane and ammonia too. This is very similar to the atmosphere currently existing on Mars and Venus today. What that basically suggests is that when our Earth first formed, its atmosphere was very much like Mars and Venus are today. Secondly, the Earth started to cool. The water vapor turned from a gas to a liquid, that's what we mean by condensed or condenses, to form the oceans. So if you remember I was talking about that comet earlier, that comet basically boiled under the ground and erupted through volcanoes. Volcanoes are a bit like the pimples on our planet's skin. So scientists believed it rained for thousands of years, and that's where our oceans come from. All the water filled in the cracks and the dips and valleys in our Earth's surface, and that formed the oceans. Now, as well as that, water is an excellent absorber of carbon dioxide. We have a bit of a problem at the moment because there's so much carbon dioxide in our atmosphere that it's turning the waters acidic, which is causing massive problems for sea life. But in our early atmosphere, it's certainly true that the waters also absorbed the carbon dioxide in our atmosphere, so both these gases went down. Stage 3, and we're really sort of jumping ahead here, but green plants evolved and they produced oxygen. It's quite a common exam question when they ask you to describe the process that reduced the levels of carbon dioxide in our early atmosphere. You would say that green plants evolved and they carried out photosynthesis, which takes in carbon dioxide and releases oxygen. The carbon dioxide that made it into the oceans was taken in by sea life or shellfish, and that's where they made their shells, which contains carbon in the form of calcium carbonate. When shellfish die and get buried under sediment and get crushed and compressed together, they form rocks called carbonate rocks, such as limestone. It's quite crazy to think that all this is the remains of sea creatures. Similarly, when plants die and get buried under sediment over many millions of years, they change into fossil fuels such as coal. So the carbon gets locked away as coal, and when we burn coal, it gets released into the atmosphere again. After having oxygen put into our atmosphere, something else changed. We developed the ozone layer. Now, the ozone layer is incredibly important to us, not for breathing in, but for protecting us from harmful UV radiation. If it wasn't for the ozone layer, the UV radiation would basically scour the surface of our planet, making it almost impossible for life to exist. So because UV radiation has been blocked by the ozone layer, complex life forms such as ourselves have been able to evolve. So present day, we have human activity and natural activity that continues to change the atmospheric composition. Human activity involves burning fossil fuels, which I've already talked about. That's increasing the amount of carbon dioxide and has been heavily linked to climate change because carbon dioxide is a greenhouse gas, it traps heat. Deforestation, well, we know that green plants photosynthesize and take in carbon dioxide, so if we're cutting them down, less carbon dioxide can be taken back in, so there's more in our atmosphere. And also, due to our growing population, we're farming more farm animals such as cattle. Now, when cattle basically chew grass and swallow it and then regurgitate it back into their mouths, something called cud, they release a lot of methane. A lot of people think it comes out of that end, but actually it's from here. Methane is also a very powerful greenhouse gas. It traps heat and is linked to climate change. But we're not completely to blame. Volcanic activity continues to chuck out sulfur dioxide, which causes acid rain and volcanic smog, and also carbon dioxide, which again is linked to climate change. In summary, we start off with high carbon dioxide and water levels due to volcanic activity. Then the Earth cools and the water vapor condenses to form the oceans. The oceans absorb carbon dioxide, and some of that will go to form carbonate rocks. Much later on, green plants evolve. They take in carbon dioxide and increase the levels of oxygen in the atmosphere through the process of photosynthesis. Then, due to the oxygen in the atmosphere, ozone layer develops. The ozone layer blocks harmful UV radiation, making it possible for complex life to evolve on our planet. Present day, due to human activity such as burning fossil fuels and deforestation, we are putting more carbon dioxide back into the atmosphere. Also, due to natural volcanic activity, there's carbon dioxide and sulfur dioxide also being pumped into the atmosphere. So if you can remember the key checkpoints involved in how our Earth's atmosphere has changed over time, you've achieved aim 2. So what's the evidence for changes in our atmospheric composition? Well, firstly, one of the most important sources of evidence come from analysing Antarctic ice cores. Every year in the Antarctic, due to continual snowfall, new layers form. So let's say I'm looking at this layer at the moment, but next year we expect a new layer to be formed. The following year, another layer is formed. As each ice layer gets compressed, air bubbles are trapped inside. Once trapped, these little pockets of air are preserved. So let's say this layer formed in 1980, whereas this one formed in 1979, and this one in 1978, and so on. This would contain air from 1980, and this would contain air from 1979. So basically, bubbles of air are trapped in the ice layers, new layer forms every year, and the older the layer, the older the air bubbles. So what we need to do is take an ice core. So what you can do is drill down and take a cross-section of the ice. We simply remove it and we analyze it. So this is our ice core, and using very sensitive equipment, we can measure the concentrations of, for example, carbon dioxide within these air bubbles. And the alarming sort of conclusion we make is that carbon dioxide levels are higher in more recent layers. The problem is no one can give an eyewitness account of atmospheric change because no one has been alive that long or anywhere near that long. So we use techniques like this, but we also have to use intelligent guesswork. And finally, we look at the experiment where we can investigate the proportion of oxygen in the atmosphere. In other words, how can we prove the atmosphere is 20% oxygen? This experiment forms the basis of many exam questions in the chemistry module, but it's dead easy to understand. So this practical can be performed in a number of ways, and I'm going to show you 2 of those ways. But remember, the principle is always the same. So, you take some water, you get some iron wool, and put it in a boiling tube and turn it upside down. You then heat the iron using a Bunsen burner, and the iron, being a very oxygen-hungry metal, will react with oxygen and the water level will rise. the water level rises to replace the oxygen which has reacted with the iron in the boiling tube. So the water simply replaces the oxygen that was in this airspace. What you should expect is a fifth of the airspace in the boiling tube should be replaced by water. A fifth is 20% of the boiling tube. So we can conclude that 20% of our atmosphere is oxygen because the air in here represents the balance of gases in the air out here. But if that wasn't clear enough for you, let's take another example. So here we've got two syringes which are sort of joined together. In the middle I've put another oxygen-hungry metal. It's really important that you use an excess amount of metal. What that means is make sure you use more than enough so that all the oxygen in this airspace reacts with the metal. If you don't use an excess amount, there's a chance that not all the oxygen will react and therefore you'll get the unrepresentative reading. So you can use any oxygen-hungry metal. Iron, copper or magnesium are commonly used in exam questions. And also expect them to test you on why you use excess amount of these metals. The answer being to ensure all the oxygen reacts with the metal. So in this airspace, let's assume that the blue represents the nitrogen, the red oxygen and the yellow argon. And let's assume the airspace has 100 mils of air, or 100 centimeter cubed. So that's the volume of air in the airspace here. Now all I have to do is gently heat let's assume it's the copper in these test tubes. As I heat, the oxygen will start to react with the copper. What you can also do is move the plunges back and forth to swish the air over the copper to speed this up. So as I'm doing this, the oxygen reacts with the copper. Now hopefully you can understand why we use excess amount of metal so that all the oxygen here does react. There's none left in here. So this chemical reaction can be summarized using this equation. 2 atoms of copper plus 1 molecule of oxygen will produce 2 molecules of copper oxide. You could adjust this equation for different metals, so you could put magnesium here and magnesium here instead if you wanted. So now all the oxygen's been used up in this chamber. A vacuum is created, basically an empty space where there are no particles where oxygen used to be. This will create a suction pulling the plunges inwards to replace the oxygen which is now gone. So if we started off with 100 milliliters of air in this chamber, now after the oxygen's gone and the plunges have moved in, we only have 80 milliliters of air left. This suggests that 20 milliliters of it was oxygen. In other words, 20% of the atmosphere is oxygen. Really simple, nice, easy experiment to prove quite a significant point. And that's how we explain the evidence for atmospheric composition and changes to atmospheric composition.